We've been working with volume by slicing, and I have another example of that for you. So it says this: using integration, show that the volume of a pyramid with a rectangular base B and a height h is in fact B times h over 3. So why don't you pause the video and try to work on this volume by slicing problem. All right, assuming that you've given it a go. Again, I already told you it's a volume by slicing problem, so I think the first order of business here is to figure out, okay, how are we going to slice up this pyramid? And to me, I think right off the bat, the most obvious choice to do is going to be slicing it like this. I think we should slice it like this. And if we now are to slice it like this, then we need to really figure out, okay, what are the side lengths of this slice? Because this is a rectangle here, and if we can figure out the side lengths of this slice, then we can multiply those together and get the area, and then we can then figure out, okay, multiply it by a little differential to get a little piece of volume, and then boom, we can just integrate all of those little chunks of volume, and then we'll end up with the volume of our pyramid. So that's where we're headed. And in order to figure out kind of these side lengths here, we should start to throw down some other notation. You can notice that B is fixed. That's the area of our base. But we can then describe these side lengths here. So we could say that this is L and this is W. And again, both of these are fixed. And then H is also fixed. So we have all of these fixed lengths going on here. And again, B is equal to L times W. Length times width is our base, area of our base. So we have all these fixed lengths here going on. But you can notice, as we take slices, the lengths, the side lengths of our slices, these rectangular slices, are going to be varying. They're going to be changing. As we move further up our pyramid, again, these lengths are completely different than these lengths here. So how do we start to describe those things? If all we have are fixed lengths and we need to somehow describe varying lengths, how do we do that? Well, the main thing that you need to recognize is we actually need to introduce a new variable. And this variable we're going to say is going to describe this height here from our vertex down to wherever our slice is. And maybe we can call it, let's call it Z. Let's call it Z. So now that we have this, I would argue that we have enough to describe what these side lengths of our slice is going to be, our rectangular slice. And how we're going to see that is, okay, I want you to look at this. This is going to be your point of view. This is your eyeball. And you're going to look at this pyramid from this perspective here. So you're going to see this side length. And what you're going to see is this triangle. You're going to see a triangle. This triangle here. All right. And the bottom length of this triangle here is going to be W. That's exactly what we have here. And then again, we have this side length. I want that in orange. We have this side length of one of our slices that we're taking, okay? And then a few last things. We know that this whole length here is our height. And then we also have this variable length now, and we're calling that Z. We're calling this Z. So using these W, Z's, and H's, we need to describe what the length of this orange length is. We need to figure out what that is in terms of W, Z's, and H's. And what you're going to find is that that is going to be W times Z over H, times Z over H, times Z over H. And maybe if this isn't feeling too good to you, you could just vary Z and see what happens. So if Z is 0, again, we're going to be at the vertex here, and we're not going to have a length. So plugging in a 0 for Z, you're going to get 0. So that's what we expect. And then similarly, if you were to have Z vary all the way down to H, you would have H over H, which is W. And that's exactly what we have right here. So hopefully that starts to feel a little better for you. And again, this is going to allow us to capture all of the lengths here as we take slices, what the side lengths of our slices are going to be. And that's ultimately going to allow us to get some area. So let's start working on that now. Again, we are trying to get the area of one of these slices here. And then we are going to multiply it by a little differential to get the volume of this chunk. So that's what we're after. So let's pull that out and start to throw some labels on it. This is going to be one of our slices, okay? One of our slices here. one of our slices. And what did we just find? We just found one of the side lengths of these rectangular slices. So we found this right here, and this we said was W, and maybe I'll just keep it in green. This is W times Z over H. And then similarly, that was looking at this pyramid from this point of view. If we were to change our point of view and look at this side of the pyramid now, we would get the same thing, but instead of a W, we would now have L. We would have L. So this length here is L times Z over H, times Z over H. So we just found that was what we were after. We were after these side lengths of these rectangular slices, and now when we multiply them together, we'll get the area of one of these slices. So last thing, again, where are we headed? We want to ultimately be able to construct a definite integral that sums up all of these little chunks of volume. But right now, we only have the area of one of these slices. So we need to figure out what differential we're going to be multiplying by to get some depth. And maybe I alluded to that a little earlier when I said, all right, why don't you vary Z and see what happens here? Remember, all of these other lengths here are going to be fixed, but we're varying Z in order to capture, where we're placing our slice. So Z is actually going to be our little differential. We're going to be multiplying by a little dz. Little dz. That's what we'll have over here as well. Little dz. So now we have all of the pieces in order to get a little chunk of volume here. When we multiply all of these pieces together, we get a little chunk of volume. So we want to integrate that. So let's start to construct our definite integral. So we're going to have the integral, and we'll leave the limits for last. So we'll fill in our integrand first. So we're going to have W times Z over H times L times Z over H, and then times dz. We're going to be integrating with respect to z. And if we're integrating with respect to z, what are our limits of integration? Well, they're going to be going from 0 all the way up to h. 0 to h. And that, again, we're going to get these slices that are going to start. We're going to start getting these slices at the vertex and start moving all the way down until we fill out this whole pyramid. That's how this integral is going to work. So now that we have our definite integral, all we need to do is evaluate it. So let's do that. Again, we can remember that we said that W times L, length times width, is going to be base. So that's going to be B. So we can fill back in B. And then we're left with Z times H, Z over H. We're left with Z over H squared. And then this is going to be integrating still with respect to Z. We'll throw down our integral again from 0 to h, and we're getting super close. So we can notice b is a constant, and we have h squared in this denominator, so that's also a constant. So we can take those out of the integral, and maybe I'll just keep everything now in orange. So we're saying that we can take b over h squared out of our integral, and then we still have the integral from 0 to h, and we're left with z squared times dz. Let me grab a little more space. And now, anti-differentiating z squared, we get z cubed over 3. And again, we're evaluating this at 0 and h. And then this whole thing gets multiplied by b over h squared. So now, evaluating z cubed over 3 at 0 and h, what do we get? Well, we get h cubed over 3. Grab a little more space. H cubed over 3, and then we have minus. This whole thing evaluates when we look at 0 here. This goes to 0, and then we're going to be multiplying by b over h squared. And what does this come out to? Well, when we multiply, we get b times h over 3, and that is exactly what we were after. Let's scroll back up. That is exactly what we were after. And just real quick, so maybe this was a new type of kind of volume by slicing problem. We did have to introduce this new variable, so maybe that added a new flavor to these problems for you. But also notice that it didn't matter what the length and the width of our base is going to be. It didn't matter the dimensions of our rectangular base. We still got the same answer. So that's also pretty cool.